All right. So should I just dive in?
Please.
Yes, go ahead.
All right. So hello, everyone. My name is Simon Vandevelde. I'm a postdoc researcher at the University of KU Leuven in Belgium. And I briefly wanted to present my work here. So Veronica and I met at ICLP this year, and I've actually been trying to get to a Prolog meeting or one of the Prolog education group meetups for quite some time now, but it never really worked out with my schedule. Um, and so I was very happy to bump into, well, first Christian and then Veronica at ICLP, who then very graciously invited me to show off my work here as well. So the work that I'll be showing is called FOLL-E, where the idea was that we wanted to teach first-order logic to children, right?
Yeah.
Oh, okay. So I have a Who Am I slide. I forgot about that. So I'm a researcher in logic-based AI, but I also have a penchant for computer science education. So for a very long time, I think since I've been 18, so for 10 years now, I've been a programming teacher for children in my spare time. First through a company that actually had rigorous coding exercises, but then through CoderDojo, which, as you might know, is more of a volunteer basis. And so now I'm the lead of my local CoderDojo. And so from there, it was only logical to start thinking about resources for teaching logic to children, because programming is one thing, but as a logic programmer, I wanted to actually teach logic to children. But I couldn't find proper resources. Of course, now I know that there are some great resources out there, but back then I couldn't find any. And so this is also something that I probably shouldn't need to tell you, but already in 1982, Bob wrote a report on teaching Prolog to children. But there, our main gripe was that it's really focused on logic programming and not on the declarative meaning of logic. That's what we were really interested in. And then there were some other works, but these are always at university level, right? So the Tarski's World, the Hyperproof, False Logic Chess, there's quite a bunch of works out there, but not targeting the same thing that we wanted to target. So what did we want to do? Why did we want to teach, pure first order logic? Well, I don't need to tell you these things. I think I can gloss over this. But the main thing that we were motivated by was the Wason selection task. So I don't know if you guys are familiar with this, but the idea of the Wason selection task is that you're shown 4 cards, and for 2 of the cards you see a number, 2 of the cards you see a color, right? So on the other side there's a number, and you get shown 4 of them. For instance, here 3, 8, and a blue and a red, and then you're told the proposition that if a card shows an even number on one face, then its opposite face is blue, right? And then the goal is to answer the following questions. Which cards do you need to check to verify whether or not this proposition holds? So I don't know if you're familiar with Wason selection task, but if you try to answer it for yourself, if you answer it, I guess, intuitively, then you'll find that your intuition is incorrect, because most people will want to check the 8 and blue, which is, of course, not true. What you need to check is 8 and red. Blue doesn't matter what number there is on the other side. And, it can be even, it can be odd. We don't care. What we do care about is that on the other side of the red card, there is not an even card, because then our proposition wouldn't hold anymore. So this Wason selection task, I cannot really explain it, but it really triggered us to start thinking about how to prime children in this way of thinking, learning that if-then expressions, right, as we use them in everyday logic or in everyday speech, I should say, actually have a logical meaning as well, something that you should be aware of when you are using an if-then expression, that we as humans can intend it in multiple different ways, right? All right. So the main difficulty of teaching first-order logic, especially to children, is that FOLL doesn't do anything. So it's just declarative statements about the world. So there's no animation, there's no sound, there's no graphics. It's very difficult to learn. And from a child's perspective, at least from what I remember when I was that age, it has scary mathematical symbols. I don't want to think about upside-down A's or flipped E's, right? So the idea was to build a better learning environment. So we didn't want to have them work in a full editor like this one. we wanted something that was more akin to Scratch, right? Which is, I think, the #1 programming language for young children. And when I say young, I mean like 8 to, let's say, 12-year-olds. Scratch is a great way to learn the computational thinking behind programming, rather than the actual programming itself, I would say. Or a similar thing is Code Combat, which is what we use in our CoderDojo. Once the children know enough of Scratch, then they go on to Code Combat, where they actually have to type, but it's still inside of this project, right? So you're controlling a character that needs to perform certain actions, and you can see animations, you can see how it runs, you can easily see what goes wrong and tweak your code and try again, right? So you wanted something like that. So our design goals were to have no finicky structure, no finicky syntax, to have a clear structure, and very importantly, to encourage experimentation. We just wanted a sandbox environment where children could try out a bunch of stuff and see what sticks. Because that to me, I'm not a pedagogical guy, but that to me is the main way that I like to learn. Just try out a bunch of stuff, see what sticks, right? And we wanted to encourage collaboration. The task that we wanted them to do, in our case, we wanted it to focus on model theory with clear feedback that was also engaging and fun. So you can already see it a bit in the picture here. So this is a picture of the eventual setup that we made. So for this, we came up with an application domain of robots, essentially, where we have these cartoony robots that can be configured, right? So each part of the robot can have a specific color, red, green, or blue, and a robot may also have a helmet or not. And just using this domain, they can already start expressing formulas over, the configuration of a correct robot. So the task that we do is actually very model theoretic. We just show them 3 good robots and 3 bad robots. So 3 models and 3, incorrect structures. And then we challenge them to find a logical formula that distinguishes good robots from bad robots. So you might see 3 robots with a right red arm, or a red arm that's red, and you might see 3 robots that don't have that. Then you know that the good robots, well, they all have a red right arm. So the formula is a good robot has a red right arm. And so we have 14 levels of this in total that ramp up in difficulty. Yeah, it starts with arms, but they start quantification and more advanced concepts in the later levels. And so to show the interactivity, the idea was that whenever a child or whenever a group of children, because this is a group work, whenever they construct such a formula, we immediately want to show the results, right? So here you can see, for instance, the good robots are on the left. I can use my cursor, yes. So these 3 good robots are on the left. And the formula that he presented to the computer counts them as correct, which is great. The bad robots, however, only 2 of them were not correct according to his formula. And this robot would still have been counted as correct, which means that his expression wasn't good enough yet, right? But there's this immediate feedback loop. You can check, oh, this is going wrong, and then you can inspect the robot a bit further, see, oh, it's because XYZ, adapt your formula, and continue on. So we came up with a full notation that was entirely blocks-based, where we, very inspired by Scratch, of course, wanted this packs and slot approach, where you can have a completely syntax-free building of your formula. And so in this case, we have a quantification where you say for each component C holds that the color of C must be red. And so in this way, your entire robot will be red. What's nice about it is it's actually fully generic. So everything in standard FOLL you can cover in these blocks, which is looking at possible expansions is a good thing to have, right? And because we feel that using a mouse does not stimulate collaboration, as you might have seen in the pictures, what we did is each of the blocks, we actually laser cut them out and we engraved them with their meanings. And so we are a Dutch university, so I only made Dutch kits. So in this image, you can see all the blocks annotated in Dutch, but essentially what you have here is you have the for any, the quantification. This one says color of circle is a square. This one says component. This is an if-then expression where you have an if and then the then. This is an and. This is an or. This is a unary predicate is a leg, right? And using these blocks, they can express all the necessary statements. What's doubly nice is that, well, using this pegs and slots approach also allows us to have a form of typing. Because as you can see, color off accepts a circle on the left, a square on the right. So they can only put body parts which are always round in the left, and colors which are always square in the right. So in this way, we can essentially what we're doing is we're reducing the number of possible layouts that you can piece together your puzzle pieces anyway. And we can reduce more errors that way. So if a child just tries out random stuff, then they can hopefully still learn something out of it. Again, I'm not a pedagogical guy, so I don't know if that actually works, the theory, but that was the main idea. And so this entire thing comes in a box where we put a small Raspberry Pi inside of the box. I don't think I have a great picture of it, but you can basically see it here on the bottom. And this is the camera from inside the box that looks upward, because on this box there's a glass pane, or well, a see-through pane. It's not glass, it's acrylic. So it's an acrylic pane where they put the actual puzzle pieces, and then the Raspberry Pi with the camera can detect the pieces, puzzle together the formula that they've put down through just some computer vision logic, and then actually run a symbolic engine internally and display the results. And so it's just a Raspberry Pi, a camera, LED backlight, and then these laser cut blocks, and that's it. So all you still need to supply is an HDMI monitor. That was also part of the idea. We wanted to have these very mobile boxes that can, for instance, be rented out by nearby schools that want to, I don't know, give FOLL-E as a workshop to their children. Then they can just pick up the boxes, drive them to their school, hook up HDMI monitors, which most schools have by now, and then they're good to go, right? There's no hassle of any kind necessary. So the actual application was built fully in Python, uses OpenCV, and then our reasoning engine as the evaluator. And I guess this actually, a picture says more than 1,000 words, right? This actually shows some images of some of the workshops that we've held at our campus, where you can see them interacting together, putting together these puzzle pieces and checking out the results, right? What's also nice is that because they're working together, there's more of a, well, I like to think that these puzzle pieces invite more collaboration, because there's not just one person using the mouse and the keyboard the entire time. Both people can put together the blocks. Of course, looking at all of my images, none of the images really support this this notion, but at least I like to think it. What's nice about FOLL-E as well is that it's also fully open source. So we really wanted it to be a resource that just about anyone can make themselves. So all the code is available online. There's pre-built SD card images, or well, pre-built FOLL-E images that you just write away to an SD card, plug it in a Pi, and you're good to go. The only thing you need is to have a laser cutter nearby. But nowadays, makerspaces, at least here in Europe, there's a makerspace in every major city. So you can just go to your nearest makerspace and cut it out for, I think, 10 euros per box, which is pretty good. And then, like I said, we're also setting up a program to allow schools to loan them out for a day. So to finish off, I have a demo video. I realize I've been talking for quite a while now. Oh, which I'm playing on the wrong monitor. Yes.
Yeah.
I have a very grainy demo video. Oh, my internet connection is failing. So I hope you guys haven't had a lot of issues with that.
May have to share the sound also.
Oh, but there is no sound.
You can play. Can play.
So can you see it now?
Yes.
Okay. So you see she's puzzling them together. The other girl is watching very intently. Now it's loading. It's showing the loading circles. And there you go. These are the results. So you see that one robot was correct of the good robots. The bad robots are excluded, but two of the good robots are also excluded by their sentence. Looking at the thing, well, I cannot by hard to say what they're placing down here, but it's already the more complex logic with an and an or. All right. So that's the main idea of the tool. Yeah, I don't have any great videos yet, other than that one. All right. Well, that actually already concludes my presentation. I just briefly wanted to share this and get some thoughts and feedback on the idea. I even have 2 thank you slides. The slides are also available online. And I should have put this URL there in hindsight, but if you go to FOLL-E.com, we have a website that has much more information about the project. And there's also, if you're into these types of things, there's also a paper at EAAI 2022, I believe, that you can read to get more the theoretical background of the system.
Thank you
Right.
very much, Simon. It's a very interesting piece of research. How young were the youngest children you tested this on?
The youngest were 6 years old. But it heavily again, I don't need to tell you guys this, but it heavily depends on child to child, right? I've had 6-year-olds who go much faster than all the 12-year-olds. I've also had 12-year-olds who go very, very slow. So it's just, I cannot fully explain it. But it might also be good to mention that I forgot to mention this. So we very regularly host these workshops at our campus to let children interact with it. And so there's 2 types of workshops. Well, there's 3 types of workshops, but we have the Children's University, which is a day where children get to come to our university and have the student life. So they get 2 courses in an actual auditorium building and then 2 workshops. And so this is one of those workshops, and those are 8 to 12. And then we also do STEM workshops with high school students where we use this as we build up to the notion of automated logic programming systems, and then we end off with this just to have to let them write some formulas of their own, and they are typically 15, 16-year-olds. So all of them enjoy it. That's the thing that I can definitely say about it. Whether or not it actually helps them reason more accurately, I cannot make any hard statements about, of course.
That was a question I was going to ask too. It would be nice to have a follow-up of
Yes.
what happens to these kids compared to similar age and studies kids that don't do this.
Yeah, maybe before and after quiz to see if there's improvement. And so one question I then have is, how do we apply this to teaching, say, Prolog or logic programming in general? Because I guess quantifiers play a role here, and there are other operators. So
I think the notion of having a physical language is already very powerful, irregardless of what paradigm you're programming in. There's these iPad apps that you can also, they teach programming to very young children, where you place blocks in front of the camera. I think it's called tangible programming. It's an entire research field of its own. And I think just having that is already a very big improvement, especially at this age. At the age of 8 years old, you don't want to have them type anything. They cannot type. So I think to make a very long answer slightly shorter, I think it's orthogonal, if I'm using that word correctly in English, as in it's more like a notation to teach it in rather than a methodology to teach logic programming. Regardless of your methodology, you could also opt for a blocks-based tangible language.
So an interesting experiment might be to try the Wason selection task after the tutorial and see if there is there are reported numbers about how many people get it right and stuff like that, if there is an increase or.
Yes, yep, indeed. So at one point we did that, but our methodology unfortunately was flawed. So we had a master's student of pedagogic, I don't know how to say that word in English, a master's student of education sciences, And there, unfortunately, the setup was flawed. So it was an entire year of doing workshops, but at the end, we figured out that we made a mistake. But it's something that's definitely still on the to-do list.
So Simon, there's something you said that it's mostly physical language, and I agreed, and that's very compelling. I agree with that. But there's also a methodology in there. You're using a model-based approach to teaching. You're teaching models by showing them instances. And that's something that we don't necessarily normally do. So that's a great.
And that's because we wanted to really have this declarative nature of first-order logic, right?
Yeah, really cool.
So we really wanted to go back to classical logic, and then you're into model theory from there. And so that's how this came to be. I should say, one downside of having the physical notation is that you're locked into an application domain. So in this case, we have these physical blocks, but they're locked into the robots. If we want to have a new application domain, then I'd have to recut blocks with different engravings. The shapes of the blocks can be the same. I can use the same markers on the other side for the OpenCV, for the computer vision system. That can all stay the same. But I'd have to get a second set of blocks to do it and build an entire new application.
Couldn't you put stickers? Could you put stickers? Sorry, go ahead.
Sorry.
Oh, yeah.
Mari.
You said that you could apply this to other domains. How important do you think the reading part is? So you have some words on these plates, but some also have icons. So how important is it for the children to be able to read? Or can you imagine maybe doing it completely with symbols?
Yes. So at one point, I wanted to have an icon everywhere, but then finding an icon for a universal quantification, that to me felt tricky. To me, it was also easier to have the Dutch words on there, because that could help me reverse engineers, or at least help the children reverse engineer what they want to say. So typically when they get to a new level, there's two phases. First, they want to just look at the robots and think about, okay, what do we actually want to express? And then they'll look at the blocks, and then they'll try to see how can we express what we want to express using these blocks that we have. And so, for instance, when the robot is entirely red and they don't know what to do, I'll try to get them to say the actual words for any, or something like every block must be red, right? And then in the Dutch quantification, or in the quantification block, it literally has the word every on there. So you can tell them, you know, listen closely to the first word you said, look again at the blocks.
And would you say the quantifier, that this was the biggest problem?
No. I mean, getting an icon representation for the quantifier, yes, that was, well, I think that would have been the most trickier one. Maybe even an if-then expression as well. How would you express that using an icon, other than using an arrow? But then I don't know how a children would interpret those expressions. But it might be an interesting research question in its own, really.
What about just using voice while they just say it? Because that's available now with pretty high quality. A combination of voice and the tactile could be very interesting.
That's true, where it tells them which icon they need to express something, and then they can grab that block. Yeah, that's certainly an interesting angle, because at one point we don't want it to have a natural language interface. We really do want the children to have to think about a formal notation at one point, and that's essentially what they're doing. They're building well, from a theoretical standpoint, they're even building the abstract syntax tree of the first-order logic formula without realizing it.
Can we explore this issue about whether you're teaching first-order logic or logic programming? Because the if-then itself is very close to the if-then of logic programming. The for-all is very close to the implicit universal quantifier of logic programming clauses. And the separation of positive and negative examples is very close to the way you train, shall we say, an inductive logic programming system. So one way to look at what you're doing might be a logic programming or an inductive logic programming point of view where you're asking the children to perform the induction by generating the conditions under which the conclusion that you want to establish can be determined. So to take another argument for why what you're teaching is closer to logic programming than to first-order logic. So if you take, for example, the robot where you have the positive and the negative examples, if you were teaching pure first-order logic, then you would treat the positive and negative examples symmetrically. You would have rules for defining when something is a good robot and something rules or sentences which imply that something is a bad robot. But if you're writing a logic program, and if you're generating an inductive logic program, you would focus on the positive and let the negative cases be simply not covered by the positive conclusion. So my feeling is that your approach might actually be simpler if you dropped your quantifiers and if you focused on a more systematic syntax. So for example, first-order logic is totally unstructured. First-order logic allows arbitrary combinations of logical symbols in a way which is not very helpful for knowledge representation, whereas logic programs force us a structure which is helpful for organizing thinking. So I would, in a way, it's surprising that in Leuven, where you've developed, the interaction and combination of first-order logic and logic programming, that you've opted for this first-order logic interpretation of what you're doing. Anyway, food for thought, shall we say?
Yes, that's certainly true. With regard maybe to the positive and negative examples, I think if you have a model theoretic view of first-order logic, then you also just need to express the good situations, and the bad situations are excluded from that. If you think about a theory as a set of formulas that a model should adhere to, then everything that doesn't adhere to that set of formulas is automatically not a model, right? But I'm not.
That sounds like minimal model semantics for logic programming.
I'm not too good in the theoretics of the entire logic field, unfortunately. So I cannot give a great answer to that. But we did discuss it more in our paper.
We go for it. Can I ask you something, Simon? That the idea that you have domain-specific symbols, right? You said you cannot use the same set of blocks for another domain because it's tied to the but that's because the variables are. I mean, I love the fact that a variable is a whole which you can fill with something, but in this case, that we fill it with a particular kind of object, right? That's the reason. I mean, you need a more general setup if you wanted to use this in many domains. The same set. Right. And don't you think that the kids would be able to handle that? I mean, just a different feeling.
So if everything would be a circle, for instance, and we didn't distinguish between components and colors as circles and squares, but just make everything a circle. Yes, there.
I'm wondering about the notion of the variable. I mean, these are 8 years old, and normally this curricula recommends that we teach variables to kids after that age, not that age, 10 or more, perhaps 11, in 7th grade, and things like that. I wonder whether you have experienced that kind of limitations in these children.
So again, it depends from child to child, but what always works is backtracking it. So getting them to explain what they want to say. They want to use the quantifier, okay. Then they know that they want to use, maybe I should share my screen again. Then they know that they want to use the component block. Okay, you might see yourself for a second. Okay, no, I think, okay, everyone vanished on my end, but that's fine. So if we look back at all the blocks that I have, oh no, I lost control. No, okay. Technical difficulties, there we go. So if we look back at all the blocks that I have, so what they want to do is they want to use a quantifier which only fits this pill shape thing. They look at their blocks, what can even go in there, right? They find this this thing which says components, and then they see that if they put this in there, there's exactly one shape left in there that surprisingly is filled in by this X. And so in this way, they use quantifications. They add a typed variable in this case, right? Because this X will be typed as a component, but they don't necessarily realize it. And then when they're building their formula, then many of the children, it just makes sense to reuse the X there. Or if they don't do it and they put left arm there, they ask a question, and then I try to urge them on to realizing that they can reuse the X there, because the X can be seen as being every component at the same time. Where it really becomes tricky is the mistake that all of them make. The very last level is robots with red arms and red legs. And what they have to say there is that for every component X holds that if the component is a leg or the component is an arm, then the color must be red. And most, if not all of the children will first try to say, for every component X must hold that. If it is an arm and it is a leg, then it must be red. Which is, I think, something really interesting to appear, that they all make the same mistake, that they use a conjunction as part of their condition rather than a disjunction, which would be correct in that situation. And what's more interesting is that it's the same mistake that my university students make, right? Incorrectly combining this disjunction and conjunction at least once until they realize that, of course, it's incorrect.
I think that's very interesting. It reminds me of an example. My first computer job was at the Institute for Social Research, and there was a PhD, there was a very senior researcher doing survey research in social scientists. He was an economist, I believe. Anyway, one of the things we had, of course, were filter statements to run to say what data to include. And he would say, the way he would teach how you use a filter statement is he would tell people that if you want one thing or the other, you use and if you want the and, you use the or. And that's how he would explain this to new people coming in. And if you think about it, there is in natural language, using or, I want this to be true, and I want this to happen and this to happen. I want to be in a situation, anyway, so there's a quantification that's sort of ambiguous, that if the quantification is different, you get the other meaning. So anyway, I think it happens even to senior PhD research people who have been thinking about this, have thought about it and been familiar with it for many years, that's still a issue.
There is an implicit parenthesizing that happens, which makes the and behave as an or when you apply. It's almost like implicit De Morgan happening once in a while that turns things around in natural language, anyway.
So Simon, I've got Simon?
Yes.
Okay, sorry, wasn't sure I was being heard. All of your examples include the universal quantifier, and what becomes very difficult is when you start using the existential quantifier. And I'm curious whether in this particular world, whether there are many cases where the existential quantifier plays a key role. The reason I ask that is that if you don't have the existential quantifier, and if you don't negate the universal quantifier, then you don't need quantifiers at all. As Bob was suggesting earlier, you could just have free variables, and they're all universally quantified. makes it a lot easier because you don't have those funny little quantifiers, and which is much harder for kids at this age to understand than universals. And if you would still introduce variables, but you don't necessarily have to have quantifiers. So it might make it might eliminate the quantifier problem, still allow you to bring variables in. I mean, many of the examples, like the Wasteland example, can be done with ground sentences for that matter.
Yep, that's true.
And you don't even need quantifiers or variables to get started. And then you can bring variables in, and you don't need to introduce quantifiers till much later, which is when it becomes more when they've understood all the basics. So I don't know. I'm just suggesting that maybe the existentials could be dispensed with early on.
Yes, so there's no existentials in this example, but it was an idea to include it in later stages or in different problem domains targeting different ages, right? So we wanted this really this generic language.
Right.
What strikes me is that the most so looking at the levels and the way that they go up in difficulty, the highest or the steepest jump isn't introducing the quantifier. The steepest jump is introducing the if-then expression. Because in the if-then, at least using our model theoretic approach with the good models and the bad models, it's difficult to spot an if-then in a good model. So the example that we have there, and I'm still not happy with it, I'm still thinking of a better way to do this level, is that every robot that wears a helmet must also have a green right arm. And then there's two robots wearing a helmet. Two of the good robots are wearing a helmet, has a green right arm. There's a good robot without a helmet with a red right arm. And then all of the bad robots wear helmets, but with a different arm color. And that level is the single most difficult level for the children to get intuitively, to figure out that this if-then means that it's only applied when there is a helmet. And when there's no helmet, we don't say anything about that other robot.
Absolutely the case. It's what we've discovered, that same exact thing. It's the if-then. It's because if-then is so peculiar. You have counterfactuals, and what do you do with counterfactuals and so forth? It makes it kind of interesting. If-then is definitely the most interesting part. So that's why I'm suggesting you don't need quantifiers or variables to really explore those issues. You can do it all without in either of those things.
Do you also try to teach if and only if sort of thing, because in Bayesian selection task, the confusion that people have is that they tend to complete the if.
Yeah.
And so essentially interpret the if as an if and only if.
Yeah, indeed. So we don't have equivalences, but it can be added. So that's one of those things where we first started from our generic language and then went to our problem domain and just cut out everything we didn't need in that case. But the idea really is that we can extend it down the line. Unfortunately, since doing the project, I've become a postdoc, and that means that you answer emails nonstop. So I haven't had time to actually extend it anymore. I mean, it's good that I became a postdoc. It's just unfortunate that I don't have time anymore.
This is wonderful, great work. Yeah.
Very interesting. Very interesting.
So one, very simple point that, you're mentioning about having to etch the text, but couldn't you use stickers that I'm sure you must have thought about it for
that you can
portability.
peel off, or have some Velcro type things where you can just peel off the Velcro, right? Yes, so those are also things that
various different types, because you have a typed language. You're going to have different circles and squares and so forth. If you didn't have types, then the stickers alone would do the trick.
Yep, that's true. Or you need domains that are always exactly typed, or you need to have a bunch of predicate variables where predicates are different. There's many things you can think about. But this is the first thing that we thought about, right? So many of our design choices were just because we felt it good at the time, and not because we're, like I said, maybe I should have prefaced my entire presentation. This entire thing is a side project, had nothing to do with my PhD, and was just something we wanted to do, right? And I luckily found time for it.
Impressive.
If I could go back, I would have, collaborated with other people.
Where do you want to go with the project, Sam?
On the one hand, there's the renting it out to schools, or just giving it out to schools, right? As loaning, that's the word. So just for free, they can come pick it up, or in the local CoderDojos, or just anyone who wants to do it. Then on the other hand, I want to do more actual, education research, see how we can fine tune it to make it better. Things like exactly the feedback that you guys are giving me. Try to test it out with actual user groups, right? But that's for the let's say near distant future, when I have more time and some nice collaborators, perhaps.
David?
Yeah. You mentioned in the introduction briefly, and the wanting to teach computational thinking or computation in there, and I don't see. Okay, I mean, how do you see computation? I don't see computation in what you have now. This is pure declarative truth, and there's no idea of computation. At least, I suppose you could think about. Well, I don't know. I don't think there's. I'm interested. Do you have thoughts about how you would want to introduce computation as a extension, as a going on from sort of where you are?
So I'm, and this comes back to my other interest. I'm a big fan of explaining logic in all of its forms to our software engineering students as a crucial thing. Well, not crucial, as a very helpful thing when they're programming code, right? So if you're thinking about writing a filter expression, well, that's just again, you can see that as a universal quantification, let's say. That's not the best example. I'm blanking on a good example, but there's many of these things that you can interpret from a logical standpoint, and to me that makes it much more clear. There's also the idea of code verification using logical symbols that's coming up more and more. Of course, 8-year-olds don't need to know about code verification, let alone code. But I think they're very heavily connected. I just cannot fully verbalize why.
Yeah, that's using logic to describe computation, I think, but it's not computation arising. Like logic programming somehow has computation arising with the logic more. Right. I mean, they're intrinsically connected more deeply than a truth condition for some program, some conditions. Anyway, I don't know.
So one case where that could begin to arise, David, it's not entirely there, is when what Simon's been doing primarily is asking the students to write formulas to satisfy exemplars. But the alternative to that is to give them sentences and to ask the students to find or do constraint satisfaction in effect. And then they have to iterate through the various different alternatives to do that. And that introduces some basic notions of computation, some systematic thinking when you're doing constraint satisfaction problems where they're given a formula and they need to understand it and use it rather than generate the formula. So that you can use the same environment to teach some of those aspects as well. Now, that's not resolution, but it is an element of a way of doing that with computation.
Yeah, no, that's a good point.
And it might be helpful to first do this exercise where you're given the formula and you figure out which one satisfy, and then move on to actually constructing the formulas. I don't know if you do that, Simon. You go straight into asking kids to, okay.
So I don't do it, but it would indeed be a great idea.
And it will actually also be an interesting study for, somebody in the education department to see if, that helps. Maybe it doesn't help.
Indeed. So for our...
And there's an in-between version of that, which is you give them the formula and give them an exemplar and say, is this an exemplar of that formula? So that's the first step. And then you say, now find exemplars. And then you say, here are some exemplars, give me a formula. So you kind of go through those stages.
Yeah, I liked very much the way you combined the universal quantifier with the X variable to fit together. And that opens a little bit a window related to how you would do it with types, when there are multiple types, with a physical representation for them, in which the USB-C that matches and the other connectors that don't match and so on. It's all over the world, of course, and for everything, it's basically physically encapsulated or defined types. And in particular, in the lambda calculus, this would be a very interesting way to also do it if you want to teach some elements of lambda calculus, not necessarily to the very little ones, but a few years later, with a similar physical representation. That just as an open research topic.
Yeah, I was very happy when I came up with well, the idea of having types being different shapes is very easy, but the idea of having the X be also typed using, the small triangle that we cut out, that to me felt very satisfying when I thought of it. Because you can apply it to every type regardless of the shape, right? So if you wanted to quantify over colors, we could do the exact same thing. Of course, we'd have a different, we'd need a different universal block for that, which kind of defeats the point. Right, okay. But theoretically, it's possible, and that was the idea, right? Theoretically, everything should be possible, and then we'll apply it to our robot domain. So one thing that we're still actively thinking about is different domains, right? Maybe domains that are more engaging for teens rather than the 8-year-olds. But I still haven't thought of what that should be yet. So for that, I'm also always open for feedback.
So there are interesting examples of bringing out the difference between the quantifiers. So one that I just recently came across is every Swede has a king and every Swede has a mom. The difference, of course, is that all Swedes have the same king, but different Swedes. So the way you code it is for all X, there exists Y versus there exists X for all Y. So it's can be quite interesting.
I think it's interesting to bring in the implicits in language use. Because other than that example Gabal just gave, also if you say, for instance, why do they always say the and instead of the or in whether if there is a green arm or a red arm? It's not necessarily because they're making a mistake, it's because maybe implicitly they're thinking, in cases when it's red, they have a red arm, and in cases where they have a green arm, this happens. The reasoning is correct. The thing is that there's a lot of implicit things going on in language. And if you could make explicit that, then there's a problem.
Yeah, it's exactly the filtering. If I want to include red arms and green arms, I just said I want to include and, but no, I have to use an or, right? The way I include red arms and green arms is I say it is either a red arm or a green arm. Then I can, so, I mean, it's.
Well, the thing is, both expressions are correct according to what you mean by them. If you use it, in cases when the arm is red, and in cases where the arm is green, this happens. That's correct.
It's the scope of the quantifier.
Well, set union.
You have to make all of that implicit in language, explicit in the formula, or at least in the explanation of the formula, so that they don't get confused.
I mean, but quantifiers are devilish. I mean, they're hard to, no matter how much experience one has.
Well, except as Bob said, if you only have universal quantifiers, then you don't need them, and then I don't think it's that hard.
But if you bring in negation, then you might be negating over, and then so the moment you have negation, then you bring in, existence. I mean,
true.
So yeah, so
to go from first-order logic to
so it shows up, and I stumble on it all the time when writing, these CAS programs. Always make mistakes.
Yeah, the hardest thing in teaching SQL is how to get universal quantification, because SQL generally only allows through negation, through double negation, and that's undergraduate students struggle with that. I struggle with it.
Me too.
So I have one question.
Yes.
So first, congratulations, Simon, for the talk, for your work.
Thank you.
So I was thinking whether you think it's feasible, for example, to in order to teach programming, logic programming to children, to create a program that performs a very, very simple task, for example, with robots. For example, make one robot get to the place where other robot is and shake hands or something like this. Or so, do something very, very simple in order to teach this notion of action and programming. So, I mean, once you have introduced the concept of robot, which I think is a very good idea because children like robots, and so maybe now make the robots do something, something very simple, some action very simple.
Yep, that's a good point. Yeah, I'd have to think about that. Well, I'd also have to find time, but that sounds like a nice next step, right? Though it goes a bit in a different direction than what we're doing now. But it's still a nice addition to the current thing. I don't know how easy it would be to do it with the blocks based, well, our tangible, our physical blocks, right? But I can easily imagine a Scratch-like environment for logic programming where you're instead of the cat moving around, you have something else moving around and interacting with things.
Yes, start with a very simple action, one action.
But that's kind of what Logo used to do. I don't know if people know
Yes.
Logo, right? But was to make it active and physically active, right? And you can do programming that way. But that's a different thing. I mean, you're doing logic, that's programming, and yes, you can do both, but they're two different things.
Yeah.
Well, it's a wonderful talk. Thank you very much,
super,
Simon. And thank you
Yes.
for the questions,
Thank
which
you.
are also very, very interesting and inspiring.
And we are all glad that you bumped into Veronica at ICL.
Yes, I'm very happy as well that it happened.
We don't have a lot of time left, only 4 minutes, but I want to ask one question. At one point, we alternated days. 1 week, one time we had it on Tuesday, one time on whatever other day. And I'm thinking it may be a good idea to just move to that model forever. And kind of at the beginning of a semester or once a year, we decide which other today other than Tuesday. So that people can maybe attend more, because some people are unable to ever attend just because it's Tuesday. In particular, one of our co-chairs of PEG 2026 cannot attend on Tuesday because she has another commitment. So what do you think about the idea of?
But are there people
Right.
who have trouble with Tuesdays now, or?
I have
Yes.
trouble 2 days, 2 quarters a year, spring and fall.
Okay.
So that's what I'm here just by, this is an accident. Normally I wouldn't be able to be here in the fall.
Okay. Sure. Definitely good idea. Yeah.
I think that way we can accommodate the most people, and we definitely want to accommodate everybody that wants to attend should be able to attend 1 day a month at least. So if you all agree, I'm going to set up a little voting scheme on what alternative day people would be able to come to, particularly those who cannot on Tuesday. That's the most important people to catch. And then we can every now and then revise it as the semester starts or whatever it is. You think it's a good idea?
Yeah, sounds good.
Okay, so I'll proceed with that. And there being 2 minutes, I'll just end with, it would be really nice if we could maybe